Hello everyone, welcome back to another Watch Me Do Math video. In this video we're going to be looking at a particular integral which is relevant to physics, IB Physics topic 9.1, that is Simple Harmonic Motion. It is going to make up, or at least this video is going to make up one video of a four-part series where I teach you all the content that there is to know in IB Physics topic 9.1. And this will cover most of what you need to know for anything to do with simple harmonic motion anyway. So they will be released over the course of now to next week on Sunday, which is when the final video will be released. This video we're going to be going over the integral, this is a mathematical video, the integral of 1 divided by the square root of x0, which is a constant, squared minus x squared dx. The reason we're going to go over this integral is because it appears in one of the later derivations of physical formulas that we work through when investigating simple harmonic motion. So I thought to make this into its own separate video and publish it before moving on to that. So this video is going to be a mathematical video that focuses on this integral. So if you're new to the channel, this is Watch Me Do Math. If you are interested in stuff like this, maths, physics, released 3 times a week on Tuesdays, Thursdays, and Sundays, hit the subscribe button and leave a comment. Turn notifications on if you want to be notified of new videos from me. So, how shall we go about this? Well, the way that you might want to do this is through something called Trig Substitution. And it is similar to U substitution, or really substitution in general, when working with integrals in maths. And I have another video titled For the Bored Student Leaving Year 11, where I go over an integral that requires the use of this technique, and I explain what it is, namely the integral of sine of ln of x dx. But to give a quick recap of what U substitution is, that isn't in as much detail as that video, which will be linked to in the description, by the way. U substitution is when you let some expression, some part of the integral here, something in terms of x, be equal to another variable. And you use that information as well as the fact that, for instance, if u is our new variable, if u is some f of x, and f of x can be anything we want, we use our creativity here to work out a solution, then du by dx would be f prime of x, right? And so du, an infinitesimal changes in u that is being summed up via integration, is equal to f prime of x times the infinitesimal change dx. So this can be turned into du in the original state, in the original integral, and anything that involves fx in the original integral can be changed into u. And then you have a new integral in terms of u, which is likely going to be easier to solve. And you can do this again and again and again, and if you have particular limits of integration, then they get converted to the u world or the v world, or however many times you substitute like that. But more detail in this video for the bored student leaving year 11, which is linked in the description. So, what would be our first steps tackling this? Well, as I mentioned, we were going to use something called trig substitution, which is an integration technique that is roughly around the level of IB higher level maths, but that doesn't mean everyone can understand it, because fundamentally it uses the same principles as U substitution does. The unique thing about it is that while U substitution may have you stuck in this u is equal to f of x idea, trig substitution centers around, for instance, in this expression, x naught squared, x0 squared, where x0 is a constant that represents the amplitude of some motion in simple harmonic motion. So this is constant. This expression is very complicated and would probably not be easily solved with a typical u substitution. But if you let x be something else, if you let x be another function, or really this can take any form if you think about it, not just the typical way of doing u substitution which I mentioned here, but you can do any kind of equivalent to get your substitution item that you're going to use. So trig substitution centers around making x equal to something to do with the trigonometric function. So like, for instance, here, I might pick x is equal to sine theta. And so this might be one example, and I'd differentiate by theta to get dx by d theta is equal to cos theta, because we're differentiating x by theta. So differentiate x, you get 1, but you differentiate it with respect to x, so you've got to include the chain rule thing. So if it's d by dx x, you've got to multiply it by dx over d theta if you want to have differentiated it with respect to theta. So anyway, and sine theta, of course, differentiated with respect to theta is cos theta. So multiplying both sides by the infinitesimal, infinitely small change in theta d theta, a change in x dx is equal to cos theta times the change in theta d theta. Alright, so that's kind of helpful, but that's not the particular substitution that I'm going to want to make with this integral. And I invite you to look and investigate why. Because we've got here some term on the bottom, the square root of some constant squared minus x squared. Now I want you to think about this square root and what you might do to simplify it using trigonometric functions. So pause the video and think about that for a minute. Now that you've unpaused the video, I'm going to give you a hint. So we're going to focus on this particular trig identity. Sine squared theta plus cos squared theta is equal to 1. So 1 minus sine squared theta would be equal to cos squared theta. Can you see where I'm going with this? 1 minus sine squared theta might, to you, look similar to this 1 minus x squared within the square root. And as a matter of fact, this x is equal to sine theta substitution would bring this square root with 1 minus x squared into 1 minus sine squared theta, or the square root of 1 minus sine squared theta, which would be the square root of cosine squared theta. And naturally this becomes, because the square root in an integral refers to the functional square root. A functional square root, that means when a square root is part of a function, you always take the positive side. Positive square root of cos squared theta is going to be cos theta. And that makes it so much simpler, because cos theta in an integral is easier to work with the square root of 1 minus x squared, for instance. In this case, at least, it is easier. So, how does this apply to our original integral? Well, we've shown how we might convert 1 minus x squared into a simpler form using trig substitution, namely this x is equal to sine theta. So it would follow logically that we could do a similar thing for a similar function. So say we have the square root of x naught, which again, it represents some amplitude, it's some physical quantity that's constant. squared minus x squared, then what do we do now? Well, the center of this relied on the fact that 1 minus trig thing squared was equal to another trig thing squared. So we want a scenario where x0 squared minus a trig thing squared is equal to a trig thing squared. It seems like this equation is a scaled up version of this equation. So what if it was x0 squared minus x0 squared sine squared theta was equal to x0 squared cos squared theta? Well, this is exactly the kind of trig substitution that we're going to use here. Trig substitution in and of itself is something that I believe is not as creative as regular U substitution, because you're limited to using these particular functions which are useful in only a few circumstances, or at least that's my impression of it right now. I might learn more as I go through my schooling, but for the time being, U substitution seems like a more creative and versatile thing to me, since trig substitution is technically a form of U substitution. But anyways, that point aside, this is useful to us in our scenario. So what is squared? What do we make x to make x0 squared sine squared theta? Well, the square root of this is the square root of x0 squared times the square root of sine squared theta. Or in other words, because it's two unique factors that have been squared, you can take the square root of both of them to find that this is x0 sine theta. So that ends up being our trig substitution, because we want this x to become x0 squared sine squared theta. So let's let x be equal to x naught, x0. Well, fun fact, this 0, I keep saying naught on habit because it's a faster way to say 0. It's got one syllable. This 0 is also called naught, spelled N-O-U-G-H-T, for those of you who are not aware of it before. So let x be equal to x0 sine theta. So how do we go from here? Well, let's differentiate by with respect to theta, so that we can get a dx and a d theta. So d by dx, differentiate x with respect to x, and then by the chain rule, we're going to have to add the differential of x with respect to theta is equal to, well, x naught is a constant, so that makes it quite easy for us to deal with the right-hand side, because we're now just looking at sine theta. And the differential of sine theta, as I mentioned earlier, is cos theta. So overall, the differential with respect to theta of x0 times sine theta would be x0 cos theta. And this dx, this thing here, is equal to 1, because that's what happens when you differentiate x with respect to x. So it's multiplied by dx by d theta, and this brings the full equation, what the full equation is telling us, to dx by d theta is equal to x naught cos theta. So if you look back to our original integral, so far we've replaced the x in the denominator term with x naught sine theta. So this gets us to 1 over the square root of x naught squared minus x naught squared sine squared theta dx. It's the integral of this multiplied by the infinitesimal change in x. But we want that in terms of the infinitesimal change in theta, so that we can apply our known integration techniques. So given this equation here, a infinitely small change in x divided by an infinitely small change in theta is equal to the constant x0 times cos theta for whatever theta it is. So if we multiply both sides by the infinitely small change in theta d theta, we'll get dx is equal to x0 cos theta d theta. So if we substitute this back into our original integral, changing dx to be x0 cos theta d theta, then let's rewrite it out with what we know now in our Dataworld Integral. And I say Dataworld because this was really a term coined by the YouTuber Black Pen Red Pen. You can call an integral being in the x world, theta world, u world, etc. When you are integrating with respect to a certain variable. It's just a bit of an easier way to say it. So dx is equal to x0 cos theta d theta divided by the square root of x0 squared minus x0 squared sine squared theta. And if you're wondering why I've put d theta on top of the fraction here, well, it's because I want you to remember that an integral is just a continuous sum of something multiplied by an infinitely small increment. You gotta remember that an integral represents these infinite rectangles under a curve, the area of the infinite rectangles, where the width of each is the infinitely small change in a variable, for instance, d theta. Right? So remember, this integral sign is kind of separate to all of this. And although the integral sign is useless without d theta, because that's by intention, you need an infinitely small thing if you are going to sum something up an infinite number of times, this d theta, it has a meaning of its own, and it's just multiplied by the function here. So d theta multiplied by this function puts it in the numerator. Anyway, if we simplify the bottom here with the identity that we found earlier, x naught squared minus x naught squared sine squared theta is equal to x naught squared cos squared theta, then we get the integral of x naught cos theta d theta divided by the square root of x naught squared cos squared theta is going to be equal to taking the square root of the denominator, the integral of x0 cos theta, divided by, square rooting this, we get x0 cos theta as well. So happily, both factors on the numerator cancel out with both factors of the denominator, and all of that is multiplied by d theta. So if this fraction simplifies down to just 1, then it's the integral with respect to theta. The integral of 1 with respect to theta, because there's nothing multiplied by d theta, you're just summing up all the tiny changes in theta, and of course that's going to get you to theta. This is equal to theta plus c, because it's an indefinite integral and we can't forget the plus c. So how do we get this back into the x world? Well, as we know, x is equal to x0 sine theta. And if we want theta plus c, our final integral, then let's take a look at what we can do. Well, let's first divide both sides by x0 to isolate sine theta on the right-hand side. X over x0 is equal to sine theta. And taking the inverse sine, or arc sine, of both sides gets us to sine to the power of -1, x over x0 is equal to theta. And the reason I prefer to write arc sine instead of sine -1, arc sine here basically means the reverse function to sine, the inverse function of sine. These are the same thing. The reason I prefer to write arc sine is because it reduces the ambiguity that you have when there's a superscript -1. When there's a small -1 here, it makes me think as if it's assigned something to the power of -1, when in reality it's referring to the inverse function. So that's why I prefer to write arcsine. Arcsine x over x0 is going to be theta. So overall, the integral of this thing, 1 over x0 squared minus x squared dx, is equal to arcsine x of x0 plus c. So c plus that. Or our final answer is arcsine x over x0 plus c. Awesome. So that's all for today. Be sure to keep a lookout for the next parts of this Simple Harmonic Motion based series. Thank you for watching. And be sure to subscribe.